Welcome viewers to the second segment of the third lecture for the online series of lectures for the course of linear algebra. Let us get started with the theorem in this segment, which is Theorem 3. So here goes the statement. If A is an n times n matrix, then A is row equivalent to the n times n identity matrix if and only if the system of equations Ax equal to 0 has only the trivial solution. So since it's an if and only if statement, we have to prove both the directions. So here is one direction. It means that we have to prove if A is an n times n matrix, then A is row equivalent to the n times n identity matrix will imply that the system of equations Ax equal to 0 has only the trivial solution. Okay. Let A be row equivalent to the n times n identity matrix I. We are given that A is row equivalent to I. Okay. Then by Theorem 3 of lecture 2, Ax is equal to 0 and Ix is equal to 0 have the same solutions, right? Same solutions. Since Ix is equal to 0 has the trivial solution only, so does the system Ax is equal to 0. Okay, so when you write this Ix is equal to 0, which means that 1, 0 all the way up to 0. This is the nth column, right? Nth column. Then 0, 1 all the way up to 0. Then the nth row of this matrix ends with the entry 1. Okay, this is the n times n identity matrix, and this is the n times 1 vector, x1, x2 all the way up to xn, and we set it to the n times 1 0 matrix. Okay, and it tells us that, so if you multiply this identity matrix with this matrix, you get this matrix, right? x1, x2, you get this matrix back, and you set it to be equal to the 0 matrix here, and which means that you only have trivial solution of this system, right? So this is what we mean here. This is what we state here, that Ix is equal to 0 only admits the trivial solution, which is this trivial solution. And since Ax is equal to 0 and Ix is equal to 0, both the systems have the same set of solutions. So Ax is equal to 0. This system must have the trivial solution only. Okay, so this was one direction. For the other direction, so we prove this direction now. Okay. So for this direction, we assume that the system Ax equal to 0 has only the trivial solution. Okay. Suppose Ax is equal to 0 has only the trivial solution. Has only the trivial solution. X is equal to 0. Okay. Let R be an n times n row reduced echelon matrix which is row equivalent to A. Okay, so we start with this system, and we assume that this system has only trivial solution. X is equal to 0. Now we know what this matrix is, A. We row reduce this matrix to row reduced echelon matrix R. Okay. Let R be the number of non-zero rows in R. Okay. So we reduce, so by finite number of elementary row operations, we reduce this matrix A to this row reduced echelon matrix R, and we assume that so after we do the row reduction, we find R number of non-zero rows in R. We assume that there are R number of non-zero rows in this row reduced echelon matrix R. Okay. Since Ax is equal to 0 has only the trivial solution Rx is equal to 0 also does not admit any non-trivial solution. Okay. All right. So because you obtain the row reduced echelon matrix R from this n times n matrix A by elementary row operations, you must have the system Ax equal to 0 and the system Rx equal to 0 to have the same solutions, right? So they will have the same set of solutions, and since Ax equal to 0 has only the trivial solution, Rx is equal to 0 will also have the trivial solution only. Okay. So we get that Rx is equal to 0. This system only has the trivial solution. Now recall the remark that we had before the statement of Theorem 2 in the previous segment. Okay. According to that remark, according to the remark mentioned before Theorem 2, R has to be greater than or equal to n. Okay. So we have seen that R is less than n, and the fact that the matrix allowed non-trivial solution were synonymous, right? So we saw in that remark that if Rx equal to 0 admits non-trivial solution, then one must have the number of non-zero rows to be strictly less than the total number of unknowns of the system. Okay, but here we have the system to admit only trivial solutions. So R has to be greater than or equal to n, the negative of this statement. Okay. Okay. Good. All right. So we must have R to be strictly R greater than or equal to n. But since R has n rows, because R is an n times n matrix. Okay. Certainly the number of non-zero rows R is less than or equal to n. Okay, because the matrix R has n rows. All right. So together R is greater than or equal to n and R is less than or equal to n imply R is equal to n. In other words, R is an n times n row reduced echelon matrix. We know that R is a row reduced echelon matrix with exactly n non-zero rows. This is what we have found. N non-zero rows. Okay. Since this means that R actually has a leading one, in each of its n rows, and since these ones occur each in different one of the n columns, okay, R must be the n times n identity matrix. There is no other option. Okay, so you want to construct an n times n row reduced echelon matrix with n number of non-zero rows. So the only way you can achieve it by putting the ones along the main diagonal. Okay. That is the n times n identity matrix. Okay. So we have found that A is going to be row equivalent to n times n identity matrix. QED. Okay, so it's time to discuss an inhomogeneous system of linear equations now. Let us discuss now an inhomogeneous system of linear equations. Ax is equal to y. Previously this was the 0 column vector for the homogeneous system. Now it's not in general a 0 column vector, it's y. Okay, and such a system is called an inhomogeneous system of linear equations. Okay, so before embarking on the discussion, note the basic difference between a homogeneous and an inhomogeneous system of linear equations. What is that? Observe that whenever you have a system of homogeneous linear equation, a system of linear equations which is homogeneous, the trivial solution is always a solution of such a system. Okay, x equal to 0 is always a solution of the system. Okay, while for this system Ax is equal to y, which is an inhomogeneous system of linear equations, there may not be any solution at all. Okay, so we will see it later that it may not admit any solution at all. Okay, whereas for a homogeneous system, the trivial solution is always a solution. So this is one of the basic differences between a system of homogeneous and a system of inhomogeneous linear equations. An inhomogeneous system of linear equations, I mean. Okay. Now let us get started with the discussion. We form a matrix out of the inhomogeneous system of linear equations. Ax is equal to y, called the augmented matrix. Which we denote by A prime from this system in the following way. So this matrix A prime is the m times n plus 1 matrix, okay, whose first n columns are the columns of A, which means that in order to write A prime, you first write A and then add a single column to it, which is just this column vector Y. Okay. So whose first n columns are the columns of A and whose last column is Y. Okay. More precisely, A prime ij is going to be equal to aij if j is less than or equal to n, okay, which means that A prime and A coincide with each other if j is less than or equal to n, and A prime ij is equal to yi if j is equal to n plus 1. We write this fact by writing A prime I n plus 1 is equal to yi. It means that the n plus 1th column of A prime matrix is just the column vector y. Okay. Alright, so now a few important observations related to this augmented matrix. Suppose we perform a sequence of elementary row operations on A to arrive at a row reduced echelon matrix R. Okay, we get started with this matrix A and apply a finite sequence of elementary row operations to arrive at the row reduced echelon matrix R. Okay, if we perform this same sequence of elementary row operations on the augmented matrix A prime, if we do this, so the EROs that we are applying on A, we apply the same EROs on A prime. We will arrive at a matrix R prime whose first n columns are the columns of R. Okay, which means that if we restrict our attention to the first n columns of R prime, we will get exactly the row reduced echelon matrix R. Okay, and whose last column, the last column of this matrix R prime column, contains some scalars from the underlying field, okay, over which this matrix A is defined. Some scalars Z1, Z2, all the way up to Zn. Since A has m rows. So there are m scalars, okay, Zn. So this is what we are getting at the end. So we are getting an m times n matrix R prime whose first n columns exactly coincide with the columns of R, and the last column of this matrix R prime is going to be given by these m scalars. Okay. The scalars Zi, where I runs from 1 to n, are the entries of certain m times 1 matrix. So we put it in a matrix form and we call that matrix Z. Now given by these m scalars, Z1, Z2 all the way down to Zm. Okay. So this m times 1 matrix results from applying the stated sequence of EROs to the n times 1 matrix Y. Remember? Y, which was the n plus 1th column of A prime, the augmented matrix. Okay? And we are applying the elementary row operations to the whole matrix A prime. And as we apply the elementary row operations, this last column of A prime, which is Y, is getting reduced to this matrix Z. Okay? That's what it's saying. Good. Now, using the proof technique used in Theorem 3 of Lecture 2, using the proof technique, employed in Theorem 3 of Lecture 2, one can show that the linear equations in the system, Ax is equal to y, okay, can be expressed as linear combinations of the equations in the system Rx is equal to Z. Okay? And vice versa. Meaning that every equation in this system can also be written as linear combination of the equations of the linear equations in this system. Okay. And hence the two systems are equivalent and they have the same set of solutions. So this system and this system, Rx is equal to Z, they are equivalent, right? And therefore, by Theorem 1 of Lecture 2, they have the same solutions. Let us see how we determine. Let us see how to determine whether the system Rx is equal to Z has any solutions. And if it has any solution at all, we should know how to determine all the solutions, if any exist. So how to determine all the solutions. If exist. Okay, so how we do that? So we know that Rx is equal to Z, this system, and Ax is equal to Y, this system. They have the same set of solutions. So if we conclude that Rx equal to Z does not have any solution, Ax is equal to Y will not have any solution either. Okay, but if Rx is equal to Z has any solution, we have to be able to find all those solutions. Okay, let's see how we do that. Let me erase everything. So let us get back to R. Okay, R is the row reducible matrix that we find from the matrix A. Okay, after a finite sequence of elementary row operations. Let R be the number of non-zero rows of R. Okay, so we also assume that the leading one of row I, okay, I varies from 1 to R, okay, this small r. So we assume that the leading one of row I is occurring in column Ki, okay, with I from 1 to all the way up to R. Then, if this is the case, then the first R equations, of of x is equal to z, effectively express x sub k1, x sub k2, all the way up to x sub kr in terms of the remaining xj's. Okay, remaining xj's. Okay. So when I say xj's, I mean that this n tuple, okay, x1, x2, all the way up to xn. So we separate from this n tuple the xk's, okay, xk1, xk2, xkr, which are the leading variables of this system. Okay, so the remaining ones here are the xj's that we mean here. Okay, so we can if you look at the non-zero rows of this system, we'll see that these leading variables xk1, xk2, all the way up to xkr can be expressed as linear combinations of these remaining xj's here, okay, which we expressed with uj's earlier, right? We denoted we denoted the free variables with uj's earlier, but now we are not using that uj's in this case. Okay, all right. The remaining xj's and the scalars z1, z2, zr. Okay, so we are going to express these leading variables here from these n tuples in terms of the remaining free variables xj's here and the scalars, right? z1, z2, all the way up to zr, because this is an inhomogeneous system. Okay, it's not so. Earlier we used to express the leading variables in terms of the linear combinations of the free variables, but here we have the scalars playing their roles here as well, because it's an inhomogeneous system of linear equations. Okay, so this is the story of the first R non-zero rows, and for the zero rows, the last m minus r equations of the system. Okay, are given by 0 is equal to, so it starts after z sub r, okay, which is z sub r plus 1, and finally all the way down to 0 is equal to zn. Okay, good. So this is our equation number 2. Let me erase this front part. And accordingly, the condition for the system to have a solution, I mean the system Rx is equal to Z, to have a solution is Zi is equal to 0 for I greater than R. Okay, these needs to be satisfied. Okay, this system needs to be satisfied, and this is only satisfied if Zi is equal to 0 for all I greater than R. Okay, if this condition given by 2, if this condition given by 2 is met, all solutions of the system Ax is equal to y can be found by assigning arbitrary values to the n minus r free variables, n minus r of the xj's, which are the free variables, that is the free variables, and then computing the corresponding leading variables, right? Corresponding leading variables. Xk i's, okay, from the ith equation. Okay, so you compute xki from the ith equation, and I varies from 1 to r. Okay, good. So it's pretty much the same way you do like you did for the homogeneous system of linear equations. But this is the non-trivial part where you find the condition under which the system admits a solution. Okay, this part. Okay, so let us take an example to see how it works. Okay, we'll understand it better if we work out an example. Let's do it. This is our second example. Let F be the field of rational numbers. We know that the set of rational numbers fulfill all the conditions, all the properties of an abstract field, and the matrix A is given by 1, -2, 1, 2, 1, 1, 0, 5, -1. And suppose we wish to solve the system Ax is equal to y for some y1, y2, and y3. Okay, some given values of this these three three scalars. Okay, So the augmented matrix in this case, the augmented matrix A prime in this case reads, so we just write this matrix A first and then attach this column, okay, to A to form A prime. So this is going to be 1 minus 2 1, 2 1 1, 0 5 minus 1, that's A, and then we attach this column which is y1 y2 y3. This is y, okay, for certain scalars y1 y2 and y3. This is our augmented matrix. Okay, so now the goal would be to row reduce this matrix A prime and convert it into a row reduced echelon matrix. Okay, let's try to do it explicitly. So this is the matrix A prime 1 minus 2 1, and in the fourth column I have y1 and 2 1 1 y2 0 5 minus 1 y3. Okay, so this is my A prime. So now I do the second type of elementary row operation given by minus 2 r1 plus r2 is equal to r2 prime. To make this guy 0, the first row is unaltered, 1 minus 2 1 y1, and the second row becomes, so starts with a 0, and this is 5, this is negative 1, and then one has minus 2 y1 plus y2, right? Minus 2 y1 plus y2, and the third row stays the same, 0 5 minus 1 y3. So see that one immediately sees that the third column, for the third column, if I subtract the second row from the third row and make it a new third row, then all these entries in the new third row will be 0. Okay, which is similar to the system 2 that we found earlier, the system which we call the system of consistency of the equation. Remember that we had some sort of equation like zr plus 1 and all the way down to 0 is equal to z sub n, right? We call this equation, we denoted it with equation number 2, right? And in this case, this will be the thing. Okay, we'll have 0 here on the left side, and we'll have some scalar on the right side, and we want that scalar to 0 to make the system consistent, okay? To have a consistent system. So for this reason, we apply the second operation again, second type of elementary row operation again, okay? And which is going to be minus r2 plus r3 is equal to r3 prime, and that will give us this matrix 1 minus 2 1, and then you have y1, you have 0 5 minus 1, right? Minus 2 y1 plus y2, and one has 0 0 0, right? and then one has 2y1 minus y2 plus y3. And for this system to be consistent, we want this guy to be 0, right? So 2y1 minus y2 plus y3 is the condition of consistency of this system. Okay. And well, but we are yet to put it into the row-reduced echelon form, and which we can achieve by doing another couple of elementary row operations. The first one being 1/5 R2 is equal to R2 prime. Okay, and that will give us this matrix 1 minus 2 1 y1, and this is 0, this is 1, this is negative 1 over 5. Okay, and then one has y2 minus 2y1 divided by 5, and one has 0 0 0 2y1 minus y2 plus y3. Okay, good. And now I have to make it 0, which I can do by this second type of elementary row operation again. 2 R2 plus R1 is equal to R1 prime, right? Which gives 1 0. Then one has 1 minus 2 over 5, which is 3 over 5 here, and you multiply this guy with 2, right? 2y2 minus 2y1 over 5 added to y1, right? So which is 5 in the denominator, and the numerator, you have 2y2 minus 4y1 plus 5y1. That leaves us with y1 plus 2y2 in the numerator, and the denominator one has 5. Okay. So this is what you have at the end, y1 plus 2y2 over 5 and this is 0 1 negative 1 over 5, and then y2 minus 2y1 over 5, and then you have 0 0 0 2y1 minus y2 plus y3. So this is the final form. This is the final form of the row-reduced echelon matrix. Okay. So let me erase everything else from here. Okay. So the consistency condition. Let me write it first. The condition for the system Ax is equal to y to admit a solution is the following. We want this guy to be 0. 2y1 minus y2 plus y3 is equal to 0. Okay. And if this condition is met, then we can express the leading variables that we also discussed in the general method. The leading variables can be expressed in terms of the free variables in the following way. So if you put this matrix into the equation form, then it will give us x1 plus 3 over 5 x3 is equal to y1 plus 2y2 over 5. Okay? And the second equation will give us x2 minus 1 over 5 x3 is equal to y2 minus 2y1 over 5. There are two equations. Okay, so there are three unknowns in total and two leading variables. So there is only one free variable, which is x3. Let us assign s, the value s, the scalar s, to this free variable x3. Then we express the leading variable x1 in terms of this free variable s in the following way. x1 is going to be equal to minus 3 over 5s plus y1 plus 2y2 over 5. This is x1, and x2 is going to be equal to 1 over 5s plus y2 minus 2y1 over 5. Okay. All right. So that the solution set is given as follows. So we are going to, the solution set is going to be a triple, right? x1, x2, x3. So the solution set is going to be minus 3 over 5s plus y1 plus 2y2 over 5, comma 1 over 5s plus y2 minus 2y1 over 5, comma s. Okay. That this triple is going to be the solution set for the underlying system. Okay. All right. So this was an example demonstrating the method of solution of an inhomogeneous system of linear equations. Now let me list the suggested exercises for you. It's from Hoffman and Kunz. Page number 15. Okay. So try these problems. Problem number 1, 2, 3, 4, 5, 6, 7, and 9. Okay. There are 8 problems. Alright, so this is the end of lecture 3. Next lecture will revisit matrix multiplication, and we'll interpret matrix multiplication as linear combination of the later matrix, linear combination of rows of the later matrix. Okay, so you have the matrix multiplication of an m times n matrix with an n times L matrix, okay, to obtain a new matrix of size m times L, right? So we'll interpret this matrix multiplication as a linear combination of the rows of this second matrix, okay? And then we'll go over the definition of the matrix multiplication, which we studied in the first lecture, and you know, and review certain properties of matrix multiplication, and we'll try to study invertible matrices. So when we have square matrices, there is this notion of the inverse of the matrix coming into play. So we'll see how to find inverses of matrices and all that. Okay. So thank you for attending the third lecture for this course of linear algebra.